To prevent the power supply from being plugged in the wrong way, we can use connectors like this one and set up some notches so that if you try to insert it the wrong way, it simply won't fit, thus preventing reverse insertion. In addition to this, we can also achieve reverse insertion protection through circuit design. Here, we use the unidirectional conductivity of a diode to prevent reverse power connection. When the power strip is connected correctly, the diode conducts and supplies power to the load as normal. The advantage of this method is that the circuit is very simple, requiring only one component. Its drawback is that the diode has a voltage drop of 0.7 volts, which results in some power loss. If the current is relatively high, the diode can generate significant heat, so this method is typically used for currents under 2 amps. You can use this method. For example, if there is a current of 2 amps passing through, the power loss here would be 1.4 watts. That is 2 multiplied by 0.7. The second type of anti-reverse circuit uses a fuse and a diode. When the power supply is normal, the power passes through the fuse to supply the load, and this side goes straight through, so the diode here is basically not in use. When the power supply is connected in reverse, the diode conducts, the fuse blows, and the circuit behind it is protected. The advantage is that there is no power loss, but once it is connected in reverse, the fuse will blow. At that point, you need to replace the fuse. This type of circuit uses a bridge rectifier to prevent reverse connection of the power supply. When connected correctly, the power supply passes through the load and returns to form a circuit. When connected in reverse, the power supply passes directly through this diode, goes through the load, and then returns. The circuit is completed through this diode. The advantage is that no matter whether you connect it correctly or in reverse, the circuit will still work. The disadvantage is that regardless of the connection, there are always 2 diodes consuming power, and each diode has a voltage drop of 0.7 volts. For example, if the current passing through is 3 amps. So, its power consumption is 4.2 watts, which means it generates quite a bit of heat. This circuit uses the switching characteristics of a MOSFET to achieve reverse polarity protection. When power is first applied, current flows through this Zener diode, creating a voltage difference between the gate and source, which turns the MOSFET on. When the MOSFET is conducting internally, its internal resistance is very low, so at this point, the current no longer flows through this path. The current flows directly through this side, which is equivalent to this path being connected, allowing the current to pass smoothly. If the polarity is reversed, the Zener diode does not conduct, the MOSFET remains off, and the subsequent circuit is not connected. Its advantage is that it consumes very little power. The downside is that the circuit is a bit complex. If the gate voltage is too high, you also need to add another Zener diode here, and add a capacitor as well.